Most of you know I'm Caroline Series. I'm the one who's been writing you a few messages in my position as being chair of correspondence. So I guess my job is to sort of filter through any comments that any of you have that you think would be better filtered rather than going direct to David or Ben Mestel. So before we start our first talk, let me just point you, there's a number of things in your pack, but you might like to just glance at the timetable here. So after our first talk, we will go straight on to some short presentations about some of the important issues that we want to then split up in discussion groups and discuss about. But our first item of business then this afternoon is a talk by Professor Nicolai Krylov from Minnesota. He's part of the Stochastic SPDE program that's going on at the moment. So very appropriately, his talk is entitled Stochastic Partial Differential Equations and Their Applications. Thank you very much.
First, I want to thank the organizers for inviting me and to give. It's my pleasure and honor to give a talk in front of such an exquisite audience. So you can read, probably you already started, that I will speak about a problem at which converge three branches of mathematics: partial differential equations, stochastic partial differential equations, and fine properties of Brownian trajectories. So in 1828, the British botanist Robert Brown noticed that microscopic particles suspended in a liquid move in a disorderly fashion. It became clear afterwards that this was due to collisions with the molecules of the liquid. At that time, actually, they were very puzzled by, not long before the microscope was invented, that everybody started to look through the microscope at various things, and Brown noticed something strange. And they would even made such experiments as to put glass of liquid with these particles in a dark closet and keep it there for 10 years and then open it and they were still moving. The characteristics of this motion, such as the mean square deviation from the initial point per unit time, depend on the temperature of the liquid, its viscosity, and other physical parameters. The phenomenon which became known as Brownian motion was thus interesting for physicists. And Brownian motion was investigated on physical level of rigor much later than Brown discovered it by Einstein, Smoluchowski, and Bachelier. Maybe not many people maybe know that Bachelier was the first who derived in 1905 the law of the maximum of the trajectory. Many people may think that it was discovered much later, but actually in 1905, although not very rigorously. The rigorous model, mathematical model of Brownian motion, was constructed in 1923 by Wiener, after whom the corresponding stochastic process is named the Wiener process. Excuse me. Actually, what Wiener constructed is so-called Daniell integral. At that time, in 1923, probability theory was not put solid ground, solid mathematical ground. Only in 1933, Kolmogorov published his famous paper about rigorous justification of probability theory. So what Wiener constructed is so-called Daniell's integral, and only somewhat later, I think about 10 years later, it was proved by I don't know who that all Daniell's integrals are integrals against a measure, and then this measure was called the Wiener measure, and the process corresponding to the measure was called the Wiener process. So what I will be dealing only with one-dimensional Wiener process, so you take one coordinate of this random moving particle. In the first place, it's a Gaussian, so the distributions, it means that if you if you take a vector consisting of coordinates given of the values of W at various times, then the vector is normally distributed. Then increments are independent, and the square, the expectation of the square of the increment is proportional to h, to the time increment. So Brownian motion is related to heat propagation and to the heat equation. The Wiener process is also related to the heat equation, not surprisingly. One of basic properties of the Wiener process is this one, that if you split time interval 0 at t into pieces of size I over n and take increments and square them and sum, then when n goes to infinity, this goes to t. This is actually very unusual. I assumed, or say it is assumed, that the increments are independent. So how could it be that you take independent random variables, square them, sum, and the whole thing tends to something non-random? Of course, the answer is that increments are independent, but when you go from one n to another n, they are not that. There is a certain relation between them. So this formula suggests that if you want to interpret dwt square, then it should be dt. So you then add here the increments of time, and then you get t. And to that effect, there is a famous Ito's formula, which says that the stochastic differential of given a function u of x, if you take u of x plus wt, then it can be written as first derivative. This is the first derivative of u with respect to x at point x plus wt dwt, and then this thing. Actually, what is written here is Taylor's formula, nothing else. Only you interpret this square as dt. Ito published this formula in 1951, and it was an appendix to his quite famous paper, and he wrote that it's a curious fact. He didn't realize that this is the basic formula of stochastic analysis at that time. Anyway, he proved it. So this in differential form, what I wrote is written like that you integrate the right-hand side of the previous formula. So there is a stochastic eta integral, there is a usual integral. What is stochastic eta integral? It is defined in the same way as usual integral, only you take the values of the integrand on the left point of the time interval and multiply by the increments of w. It turns out that this thing makes perfect sense. And for us, the most important property of the eta integral is that its expectation is 0. So now if you denote utx as expectation of ux plus wt, then by taking expectation here in this 1, 1, you'll delete this stochastic integral. Expectation of an integral is the integral of expectation, and so you come to this conclusion, which is the same as this one. Derivative in time of v is 1/2 of derivative of the second derivative of v in x. This is the heat equation. The solution is known. And well, so this is the solution. Then if you look at the definition of v, definition of v. This is the one. Expectation of u of x plus wt. And since the distribution of wt is known, it's a normal distribution with this density, then you may wonder, and then what? What did we achieve with this one? And that's what I'm saying, that one can easily derive this result differently. However, there is a different implication. So, this maybe I will repeat it. This is u of x plus wt is u of x plus 1/2 integral from 0 to t d to x u of x plus ws ds and plus integral from 0 to t dx u of x plus wt ws dws. Now let's introduce a different function. This is 1, 1. U of tx, this is random function, u of x plus wt. Then this formula over there means this thing. This is the differential form, and I wrote there in the integral form. This one will become d2x v of sx, and this one is dx v of sx, and this is v of tx. So then you get this formula, and this is the simplest stochastic partial differential equation. This is stochastic, stochastic because of this term. This is partial derivative, not such partial because it's one-dimensional, so the usual derivative, but still no derivative in time. More general SPDEs, how they arise. What I want to show is that the coefficient here is 1, and this is 1/2. How about different coefficients? And more general, they arise in the following way. This is the Ito's formula when function depend also on t and x. So then, in the differential with respect to dt, there will be derivative of u with respect to t. This is the square d of this one squared, and this is just a derivative sigma dwt. So in this way, what you see is that if you have a function u satisfying this equation, the heat equation is the right-hand side, and you introduce a new function by shifting the argument by sigma wt, then v will satisfy this equation, sigma square, which is coming from here. There will be derivative of u will have 1/2 will become 1/2 d2x u, and it is here, which is the same as v. And this is the most almost the most general SPDE in one variable. What is missing here? First order terms, first order derivatives of v are missing. There is no 0th order term here, no 0th order term, and the most kind of crucial drawback is that sigma is constant. It's non-random, doesn't depend on x, and doesn't depend on t. But still, not far. And if you want to have an introduction to the theory, then it's quite enough. If the right hand side is 0, then I repeat the formula which was before. So if you have the solution of the heat equation and you introduce this formula, V by this formula, then you will have dV satisfying this equation. The coefficients here 1 plus sigma square, and this is sigma. Now, if you introduce u of x as the initial value of u0, then what you get, this is the definition of V. Then when this guy is fixed, say this is y, then we know from before that it's an expectation of u at point x plus y plus bt one-dimensional linear process. And then you plug in instead of y this guy. And let me make it sigma wt. What is here can be written in the following way. It is a conditional expectation of ux plus bt plus sigma wt, given that you know the trajectory of w on the time interval from 0 to t. Say if you don't know any probability, and I'm saying that wt and bt are independent, so values of wt doesn't affect values of bt, and I'm saying find this conditional expectation. I give you the trajectory of wt, then find this conditional expectation. What would you do? Just fix this thing, find the expectation, and then plug in this thing in the result. So, and that's what is reflected in this formula. This expectation, conditional expectation given something, is known to be the best mean square estimate of this something, given call them observations. We see that conditional expectations satisfy an equation, and no wonder SPDEs arise in filtering problems. In filtering problems, when you have two-component diffusion process, you observe one component and you want to estimate the first component. Conditional expectations arise, and here is the conditional expectation. And this is, to me, it's the right way to look at filtering problems. They also arise in quantum field theory, population and genetics, superprocesses, and many other areas. If you don't know what superprocesses are, you're lucky. Now, now I want to speak about fine properties of trajectories. This formula gives a probabilistic representation of the solution to Cauchy problem for the heat equation. How about solutions of the heat equation in other domains? And here we take C is the set of all real valued continuous functions x given on 0 infinity. We fix capital T, here is a capital T, and consider domains my xt will always start from the origin, so this is the t-axis. Somewhere there is capital T. This is x-axis. We will start from the origin, and this is my domain. Curvilinear cylinder. Not such a cylinder, but not a cylindrical cylinder. And we will be talking about this boundary value problem. So the heat equation, although time derivative is not on the right but on the left, so actually we change. If you so the boundary data will be given here, and not down there when t was with a different sign. Actually, once I was given topics course in PDEs, in partial and parabolic equations were there, and I was considering dt always on the left with this sign. And after a while, one of students came to me and said that it's not a parabolic equation. He was very much surprised when I told him that you just change t to minus t, and then it takes the form you like the best. In connection with this, I remember a nasty joke which Safonov once played on his students. You know this equation UTT, hyperbolic equation. This is t-axis, and this is x-axis. And usually what do you do? You give the initial value of u and the initial value of its derivative in time on this axis. And what he did, he gave u of t0 and ux of t0 on this axis and asked to solve them. Nobody could, because they couldn't realize that t and x have nothing to do with time or space. They're just variables. I liked it very much. Okay, there is a probabilistic. So we have G on top. Say U capital T X is G of X, and we want to have a probabilistic representation of the solution. And this goes in the following way. So you want to know your solution, say at this point Tx. What you do, you issue a trajectory, say x plus nu bt. Bt is a Brownian motion. And define first exit time from this domain. It could be here, it could be here. So tau of tx is the first exit time actually when s plus t, and in time it goes uniformly up, and in x is x plus nu bs. First time when this is not in the domain, then you take your function g at this point and take the average, and it turns out that this is the best candidate for the solution. I am writing this quite easy fact that V is infinitely differentiable. Easy if you know something. If you don't. However, the issue of the boundary behavior is extremely delicate, and it's not everything is known about this. The question is, say, by the way, I draw G only here, but actually G is given everywhere. So U of T xt, this is my trajectory xt, is given also as G of T xt. And the point x0, this point on the boundary t0 x0 is called regular if for any continuous function given on the boundary g of t x0, you have that your solution tends to the value of g at this point. There is a probability criterion for regularity. And the criterion says that the point is regular if and only if, with probability 1 from this point, this process exits immediately from the domain. Probability that tau is bigger than 0 is 0. Actually, if it's only less than 1, it's already 0. There is a so-called 0-1 law. And then there is a corollary. And that if this happens, I will draw another picture. If you have a point, or better something like that. If you have a point on the boundary, and it doesn't swing to the left too much from this point. Actually, let me draw this is a, this trajectory is c square root of, let this be just the origin, square root of t with minus. If your trajectory is here, then the point is regular. And I give you in the proof. And the proof is quite short, but how about me proving it? Still, this is one line actually. The probability that tau is bigger than h. If tau is bigger than h, then at least x0 plus nu bh is in the domain. Is in the domain, meaning that it's bigger than x t0 plus h. Then this probability is the same as the probability of mu, let me write it fast, square root of h b1 bigger than x t0 plus h minus x t0. This is x t0. I replaced actually bh with square root of h times b1. They have the same distribution. These are Gaussian random variables with the same mean and with the same variance. So then this probability is mu b1 bigger than x t0 plus h minus x t0 over square root of h. And we know that this guy bounded from below. It cannot tend to minus infinity. But then this probability is less than 1. So this probability is less than 1. So the probability that tau, and independent of h. So when h goes to 0, it's still less than 1, less than a constant, less than 1, independent of h. So probability that tau t0 x0 bigger than h is less than a constant, less than 1. When h goes to 0, probability that tau bigger than 0 is less than a constant, less than 1, and then it's 0, as I said by. Okay, then now there are some comments about Laplace equation. For the Laplace equation, the same issue arises, and there was a famous Wiener test with, involving capacities when the point is regular or not. I would call actually Wiener test useless, because you never can, if a domain is complicated, you never can find the capacities of the complements and this and that. And then Landis did something for parabolic equations, and Evans-Garepi in 1982 actually generalized Wiener test for parabolic equations. There is Hinchin-Petrovsky criterion. This is the one, whatever. But what is interesting in this criterion is that if this limit is less than nu, and nu was in the equation, and the equation was du dt plus 1/2 nu squared d2 u dx squared equals 0. So if this equation is less than nu, then the point t0 x0 will be regular for this equation right there. But the criterion depends on nu, and in this way you see that points which are regular for one nu are not regular for a different one. This never happens for elliptic equation with constant coefficients. Non-degenerate elliptic equation with constant coefficients, all points of regularity are all the same. So parabolic equations in this respect are quite different. And then there is a theorem the theorem says the following, that assume that you have this equation and your curve is regular, and even more than that, it's Hölder continuous. That solutions of this equation, and g is assumed to be 0 on the boundary actually. This is 0 on the lateral boundary. And we are assuming that u takes the 0 boundary value with as x with rate x to the lambda. So when you deviate from x t0 by x, then the solution is x to the lambda, less than x to the lambda. Then it turns out that your boundary function satisfies this inequality. The theorem is simple, and actually I intended to show how to prove it, but let me not do it. Quite elementary, actually. If you know the maximum principle, you don't need to know anything else. So if for some nu 0 the trajectory xt is regular, then this holds. But then it's the trajectory, this trajectory is regular for any nu. That's what I stated before, that if this holds, then probability is less than 1, and the curve is regular for any equation. So, and this will this is the theorem under the assumption of the previous theorem, assuming that for nu 0 your boundary curve is regular, then it's regular for any nu which is less than nu 0. Say regular means, I'm just repeating. Now the question is u Hölder continuous on the boundary if this holds, and g is smooth and 0 on the boundary? And nobody knows the answer actually. And actually I think that you need more conditions on the boundary function xt. Now what does it have to do with define properties of the Wiener trajectory. Now we are back to stochastic partial differential equation. There are A depending on t, sigma depending on t. Forget about the dependence on time. Let them to be constant. What we assume is that A is bounded. Well, is a constant, it's fine. And we also assume this thing, that A minus 1/2 sigma square is bigger than delta. You'll see in a moment why this condition is necessary, actually. There is a theory, LP theory for such equation, which says that they exist solution, they exist unique in some spaces. In spaces, bold face H gamma pt, this is LP, space of functions defined on omega. Omega is the set of all events, elementary events or whatever. This is time, and H gamma p is the space of functions which have gamma derivative summable to the power p with respect to x. Existence in such spaces, and there are embedding theorems which we'll use, although I don't state it quite precisely. If gamma p is bigger than dimension, dimension is 1. I am sorry. Yeah, well, anyway, I can correct all of them, but you can imagine. Then the solution has gamma minus 1 over p continuous derivatives in x, which are summable to power p. And if this holds bigger than d plus 2, so 3 actually, then there are that many continuous bounded derivatives, continuous and bounded in t and x, and also soup of these derivatives is summable to the power p. Well, now how about equations in domains? Here is a unusual trouble. So let's consider this equation. dtu is d2x u, and we are considering it's x from 0 to 1, and say t on 1, 0, 1 xt, and with boundary condition, with lateral condition, so t0 is just 0, and no doesn't matter what on the bottom, g of x, say non-negative, non-Venetian. And I forgot, this is actually, excuse me, this is du dt plus dwt. Random right-hand side independent of x. Solution of this equation can be written explicitly very easily, and if you write it explicitly, you will not see the following property, and the property is that this solution cannot have bounded derivatives bounded up to x equal to 0, which is very easy to see. Write what this means at point when x is 0. The integral from 0 to t d2x us 0 ds and plus wt. This is just integral form of what is written there. Plus. This is 0, it's our boundary condition, this is 0. So you see that Wt is the integral from 0 to t d2x us 0 ds. Oh! Yeah, you know, plus or minus doesn't matter because it cannot hold. Anyway. So Wt is a differentiable function, but you remember the main property which I told you, that sum of squares of increments is t. If you take sum of squares of an integral and then let the partition go to 0, then the result will be 0. And it also say well known that Wt is nowhere differentiable. It cannot be written as this integral. So even in this situation, you see that there is trouble, that if you want to solve this equation in functional spaces, then you have to allow derivatives to blow up near the boundary. Okay, so we take sigma square less than 2, which I'll explain why, and consider this equation. There is a way to understand this equation, actually understood in the sense of generalized function. So you will multiply by a test function, formally integrate by parts, and you require this. Okay. Phew. Okay. There is some complicated formulas, but the result of this is the following, that if you can take R is the power of summability, which was before P. If there is parameter eta, which is bigger than 2 over R and less than 1, and theta satisfying whatever, then this is finite. And we want our solution F, solution of this equation, to vanish when x is 0. We want it to vanish. It means that you want to make this exponent less than 0. This is minus 1, and this one is minus 1. Theta over R is between 1 and this one. When R is big, this is almost 0. So it's not that clear that you can make it small. Eta you can make as small as you like. 2 over R when R is big. But if you analyze this thing, then it turns out that you can have this inequality. This will be finite, epsilon as small as you like, if beta is this one. And beta is bigger than 0 if and only if sigma square is less than 1. So it's a simple argument. The argument which when it was discovered, then I believe that actually then it gives you a Hölder continuity of your solutions up to the boundary. Then I believe that I can somewhat improve this, apply a different technique, and make obtain the same result when sigma square is less than 2, and this is natural bound for sigma square. But now I will tell you that actually it's impossible. It's possible, but it's done absolutely differently, and the result is upsetting, I would say. Natural approach to this 3-1. 3-1 I repeat it here. And natural is the following. Why don't we introduce the function which we already saw a few times, shift the argument. Then it turns out that if F satisfies this equation, then U satisfies this equation, 1 minus sigma square over 2. And this is deterministic equation. And you see if sigma square is bigger than 2, then dut is equal to minus something d2x u. And this is the ill-posed heat equation. This equation is ill-posed. That's why when we require sigma square to be less than 2, this is just a natural assumption. But the domain in which we are going to solve this equation is random now, because x minus sigma wt should be bigger than 0. So this becomes our random domain. For each trajectory, we want to solve the equation. Okay. Now, so our question is when this holds, this inequality holds for small x. And crucial observation here is that with probability 1, U is Hölder continuous on the boundary if sigma square is less than 1. That's what I said before. But then when sigma square is less than 1, we can estimate even f of tx over x to the certain power, expectation of it, and sup with respect to t and x. So U is Hölder continuous if sigma square is less than 1. By theorem 2-4, with probability 1, then this holds. And this is a fine property of the Wiener process, that with probability 1 for any t. So there is a set of full measure, full probability such that for any t, Wt doesn't deviate from t0. This is minus h is okay, because the time is in a different direction. But plus or minus h doesn't matter. And now the corollary, which I stated, says that with probability 1, our f actually tends to 0. Now, how about Hölder continuity? I will state Hölder continuity and I will finish. So, how this result was obtained? What we did, we applied the SPDE theory for small sigma squared, then got Hölder boundary regularity in random domains, added PDE theory, and obtained this result that this holds is obtained from the theory of partial differential equations. That if it's regular, Hölder regular, then this holds. So adding PDE theory, we obtain fine property of the Wiener process, and from here we obtain boundary continuity, not Hölder continuity. And what about Hölder continuity? Is the following. So you take this equation, and I will stop here. Then there is nu depending on sigma, such that this holds. With probability 1, it is Hölder continuous. Now, what is nu? The largest value of nu is unknown. There are estimates, although if you take nu of the mu is a number bigger than 0. If you take nu in this form and epsilon, this is the one. And when sigma square is close to 2, then you see you have here 1 over 2 epsilon with minus. It's extremely small number. And it turns out that if you take nu here in this formula, then the left-hand side is infinite with probability 1. So when sigma was less than 1, nu was a decent number. When it's bigger than 1 and less than close to 2, it's just invisible. And I was asked to finish early, so thank you for your attention. Everything is clear. Good.
Let's thank Professor Krylov again, and then perhaps we can move on to the next part of our program. So thank you very much.
Thank you.